Uh, Hello, my pleasure to give this talk on the Adamar-Bergman convolution on the half plane. This talk is based on a joint published work with Professor Alexei Karapetyan here, who is the expert on the subject. So I was thinking more about giving some kind of comments or remarks on it, leaving this survey type talk to Professor Karapetyan. And I'm writing Southern Federal University because this work was actually done while I was here. So let's see what happens. Let's have a look at this, the Adamar-Bergman convolution on disk. If you think about this formula here, the Adamar product we know from matrices, and we know a notion of Adamar product, for example, for generating functions, about making a pointwise product. So if you think of function g and function f in unit disk, expand it in a Taylor series and make the product, this would be the integral representation of this expansion, capital A being just integration with respect to area, so dx, dy, or dw, dw dash if you want. And already in their discussion of a joint paper of Karapetyan and Samko 2020, they needed this integral to be understood in the improper sense. So you see this integral is understood in terms of you cut away from the boundary of the disk and then you limit it to 1. So a question posed by Professor Karapetyan is that what happens if you think about its analog for the half plane? So this capital pi is the half plane, and just as we saw in Buffetov's talk in relation from D and R for the product, it's natural to think about its analog as a sum. So if you have absolute value of z smaller than 1, you multiply it, you're still in disk. In half plane, you add it, you're still in half plane. Okay, so this is some animal. This is something just written out of blue just by analogy. Why would you need that is a question that comes first. So one reason we would think about them is, of course, Bergman type power operators. So you think about this F, you see it's coupled with Z plus W dash beta, or these type of operators that we introduced, Bergman type exponential operators. So you can see an exponent down there. And this makes sense. For example, if you think z to the n, a function which is natural to consider in disk, when is its absolute value constant? The places, the points where it is constant, there are equidistant from the boundary of the disk. Now this exponential function, the same for it, it's equidistant from the boundary of the half plane. But if we look back at this thing in the most general terms, the question is, how do you interpret it? We had these things about this type of operators written down, for example, in talks of Suslina and Lyalinov, and it was said this is just formal expression. It needs to be interpreted, and we could interpret it in a way, quite a precise way, but a convoluted way, I would say, in terms of the Adamar product of Laplace transform pre-images of these functions. And then it turns out that it exists in non-weighted Bergman space and is commutative. And the non-weighted Bergman space is this weighted Bergman space, but without the weight. So the Bergman space would be, if you take a holomorphic function in the right half plane, you think about its L2 norms along the y-axis, and you temper the growth of the L2 norm by, say, x to the alpha. So here is some kind of our poster result. But as we go on, we could talk about results, how these operators map Bergman spaces, and these are results correspondingly. So this operator on that operator maps a weighted Bergman space to another weighted Bergman space. So we could come up to results like that too. Now, one thing is Okay, we understood. So one reasoning for discussing things like that is this integral differential type of things, but there's another justification for that too. So because people think about this applied things and so on, I was just googling this JPEG thing in images when you have this JPEG format. So one way they archive information is that so you have this image, it's a function, at each point it's a value. They make the Fourier transform. When they go to the Fourier transform, this is a psychological effect that most information that our eyes perceive in an image is concentrated on lower frequencies, and higher frequencies things are kind of not very important. So somehow our eyes cut off, roughly speaking, higher frequencies and concentrate on lower ones. So if you do the Fourier transform trick here, it would correspond to pointwise product, and you think about the other function as some kind of cutoff function. So a natural question would be, once you cut off, what class of functions turns into what other class of functions? Here's some other thing to think about, except so we concentrate on Bergman spaces. Now, as long as techniques is considered, see what happens in a disk. You have Taylor series. You have a function, you expand it in Taylor series. If you think of Bergman space in a disk, you have a function, you expand it in Taylor series. You want to phrase conditions like that in terms of Taylor expansions, and things like that happen. For example, the non-weighted Bergman space would be sum of an squared divided by n plus 1 converges. Whatever, but it's phrased in terms of necessary and sufficient conditions, in terms of Taylor coefficients of these functions with equivalence of norms and everything. What should we do for the half plane? The Taylor series does not converge everywhere. It's a half plane. So what is the thing to be done there if you cannot do the very first step already? So this is a question that happens. And another one is still, could you think about something like that? You cannot write a Taylor expansion, but could you feel a Taylor expansion? Here's the way we think about it. So you have a function in a disk, you have its Taylor expansion. You multiply that function by, say, z. If you multiply by z, so instead of fz, you have zfz, the Taylor expansion gets shifted. So you can tell how these coefficients change, and you can tell whether this new function will be in the Bergman space or whatever space it is that is phrased in terms of Taylor coefficients. Could you do the same for this space? So you have a function which is in a weighted Bergman space. You multiply it by z and say it's in a different weighted Bergman space. What could you say about the original function? So just it's like a convoluted way of thinking about power series. Like, what happens? How does multiplying by z operator works? And here we have a result you can see quite a convoluted one. So if f is in a alpha, z times f is in a different f alpha, then we can say something on f on top of that. So how do all these things work? If I may, I wanted to complement these results rather than kind of emphasizing on their being new or comparing to new results, to emphasize on some technical tidbits, лакомые кусочки, especially once we have students here about how is this technique working? How can we translate something that reads in this convoluted way into something that's like, oh, this is quite familiar to me. So this is something that when you ask specialists, they say, yes, of course, it's like that, but this is not that runs on top of mind. So some kind of things that I wanted to emphasize. I'm not sure you can see that, but this is the formula I like very much. So 1 divided by z equals integral from 0 to infinity e minus zx dx z positive. So here's what happens. In a disk, you want to get this Taylor series expansion of analytic function. How do? You write the Cauchy integral formula, you take this denominator thing, expand it in geometric series, and you have it. how do you do the Fourier integral? You don't want to do it the Fichtengauss way, like you have the Fourier series and pass to the limit. You can do it in a different way. You take a function somewhere on a half plane. You can still write a Cauchy integral formula over something like semi whatever. There's still this kernel down there. And you can express the Cauchy integral kernel in terms of Fourier kernel using this formula. So, of course, there are technicalities to prove everything, but the Cauchy integral kernel is related to the Fourier integral kernel. So this translation allows you to pass in quite a natural way without referring like, let's try a Fourier transform, but just directly to this Fourier transform. And of course, me being a real analyst, I call Fourier transform. People in complex analysis have many terms for different things, like they have Laplace transform, they have Mellin transform, they have Borel transform, and everything is to be respected in which condition we talk which. In this case, we have Laplace transform. But that's the translation. And so once you have this translation, you can translate facts about Bergman spaces by using this Laplace transform into facts about weighted L2 spaces, because Laplace transform pre-image of weighted Bergman is weighted L2. So you can just phrase things there and get your results there. In particular, if you think about these things, so multiplication by z corresponds to differentiation for Fourier pre-image. So what you have here is the Fourier pre-image belongs to one weighted L2, its derivative additionally belongs to some other weighted L2. What can you say? We feel something like Sobolev there. And it's actually there. It's called a Caffarelli-Nirenberg type inequality. So all we needed to do is just to translate it. So a question that is phrased in terms of this analytic function multiplying by z and so on somehow ends up being some type of Sobolev type inequality related thing. So on its own, getting this result would be highly non-trivial, but once you understand the translation, it just becomes a thing of translating from one subject of mathematics to another subject of mathematics. And then, once we go back to this, if we think about this in terms of Fourier pre-images, in this case, it still doesn't help you much, because if you formally try to write this thing in terms of Fourier pre-images, you get something. You get integral from 0 to infinity, ft gt, this is f pre-images, e to minus zt divided by 2t dt. Whatever, the thing is, this doesn't necessarily converge. So we do this trick. The trick is to write this integral of one variable formally as an integral of two variables. So it seems like we are convoluting things even more. But how do you turn one variable into two variables? The delta function helps. So it's delta t minus s. T equals s, haha, you go back. T is not s, you erase this. But this is a double integral written in a very formal way. But now you can interpret this thing, the delta function, as a functional acting on the space of test functions. And now you go to that area of Schwarz's book and you can work with that. So this thing exists in a very convoluted way in terms of Fourier pre-images and functionals and so on, but it exists in that sense. And it's commutative, so we could prove things like that. The thing is, once these things start making sense, we not only get results, but we also get questions, which somehow become like very nicely formulated. And once we get questions about these distributions and test functions and things like that, you go to the, you go to this library, you search through it, many questions are not answered. So for example, these translations that I already told you about, weighted L2, once you turn to Laplace transform, it becomes weighted Bergman. There is a whole theory of relating a function, which space is it in, to which space its Laplace transform is in. It's called Pelley-Wiener theory. For example, if you have compact support, its Fourier transform is exponential growth and so on. The thing is, we end up with classes of functions whose Fourier transform we cannot fully describe, but we desperately need it. So, for example, the class we came up with, if I may write with some either, this is black. Okay, so this is a class somehow naturally appeared for us, is a class of functions of sub-exponential growth. I mean, we all know sub-exponential growth, but there's a caveat. So it's like that. Ft e to the minus epsilon t, so you temper it by an exponential, belongs to CL1 0 infinity. So not only we impose a condition at infinity, but also close to 0. So for example, for all epsilon. So this is a well-defined class. So a function which is locally in L1 on this right semi-axis is tempered in this way. So it's a condition on the whole half plane, not just as t is large enough. What is this? I mean, okay, one can give some necessary conditions, one can give some sufficient conditions right away. That's understandable. One can search for that. But can one describe this precisely? For example, in terms of probably the decay of functions? There are closer classes like that, which could be described in terms of decay, like as z goes to infinity, or once you cut over this fixed x and this y, it should be L2 here, or whatever. But a natural class of functions. So what would it be? It's a complete description of its Laplace transform. So questions like that arise here from a seemingly complex analysis operator theory thing. So why not we end up with an open question? Thanks a lot.